Hello again, everyone. This is the real Pert again, coming at you live from his underground bunker. This is day 2 of your virtual learning experience, and I'm going to share my screen out now. So there I am again up in the corner. Let's get rid of this window. Just a reminder before I start that tomorrow on Wednesdays through the end of the school year, from 7 to 9, I will be available online in a Zoom meeting, which I'll invite all of you to join via your email. So you'll just click on a link and I'll admit you to the room. That'll put you in a virtual hold room, kind of like a jail cell. And then I will admit you and you can say just whatever, hello, how you doing? I've got a question. Can you help me with a calculator? Whatever your situation in life is, I will try to help you. Also, I want to remind you to check the document, which is the only post so we'll go to a class here that you'll see. I'm going to try to delete out old posts, so you're just going to see one post with the most recent message that I need to get to you. And also, you know me updating notes. You need to look back at that. So I updated this first note packet. I think I'm done now. It usually takes me a couple of times, but we're going to be using both of these today, so have them readily available. And I think that's all I need to talk about as far as business is concerned. I know some of you are concerned about like your calculator situation, and I will say that's not going to be an issue just because you don't have, an 84 plus. You just need to learn to work online and use online calculators, or buy the one that I showed you. Okay, on Amazon. This is great. This 36X Pro for $19. That is a great calculator, inexpensive. All right, without further ado here, we're going to start up day 2. The main thing that you need to walk away from this on is that logarithms and exponentials are opposite or inverses of each other, and they are used to solve the other one. And an even bigger idea is that, let's say we're trying to solve this, we use logarithms to pull exponents down, either to solve an exponential, or when you're just dealing with logarithm functions, to pull that exponent down and to graph it. And so that makes logarithm functions extremely useful for large values and small values. And I'm actually going to lead off today after a brief review of yesterday's work. So here's the steps that you would do on this: log base 3 of both sides. And then that leaves you, so log base 3 of 3 is 1. There's a reason that's true. Has to do with this, log base 3 of 3. So notice this over here. This is a big idea. So 3, the base is 3, so the first power equals 3. That's inside there. So that's always true. Log base of some number of the same number is 1. That's a huge inverse concept. And then the answer to the right here, and this is where everyone gets nervous about, I don't have a log base key on my calculator. Don't worry about that. Worry about these steps needed to solve that. Now, moving forward to today's work, which is solving logarithm equations. And so you're going to need this here, and actually the second page in this. So this is the number 2 notes in this little document here. So you need this, and this is going to be our workspace here. And also this, which I have redone this, so re-download it. And I promise I'm done after today. There will be no more changes. And I want to lead off with a couple of great examples of where are logarithm functions even used. We've talked about linear functions. We've talked about quadratic functions. We've talked about exponential functions and how you can, I'll put this other screen up that has this, and how you can tell, how do you tell you have an exponential function? Well, you keep multiplying the y values by the same number and over and over. How do you tell you have a linear function? Well, you keep adding the same number to the y values over and over. How do you tell you have a quadratic function? That has to do with something called second differences of the y values. There's all these ways of telling whether or not you have a particular function. What about logarithms? Actually, I need to say this, logarithms are probably one of the most used functions in the world. The reason for this is that logarithmic functions can handle inputs, so x values, that are either extremely large or extremely small. And the reason for that is the whole idea with logarithms is it pulls that exponent down in front of the log. So if I took log of 10, so base 10 of 10 to the 5th power. Oh, I got to put my overhead back on here. Just let me minimize that. So if I was taking log base 10 of 10 to the 5th power, so by the way, if you don't have a base written, that's assumed to be base 10. This equals 5 because that 5 comes down in front, and then log base 10 of 10 is 1. We've talked about why that's true. Okay, because 10 to the 1st power is 10. So that's always log base any number of the same number as 1. This is very useful. 10 to the 5th is 100,000? Yes. That's very useful when we're dealing with data inputs that are extremely large or extremely small. So as a couple of great examples here, and I'm going to put my other screen back up because it's just a little bit easier to see, are the Richter log model and the pH log model. So Mrs. Berry, this is a little bit of teaching for you. So Mrs. Berry came up to me last year, Pert, why haven't you taught these children about logarithms? I was talking about pH today and they all looked at me so strangely. So this is for you, and hopefully we can get some understanding of what's going on. For any logarithm function, I'm looking right here, right now. The idea is that whatever the base is, so for the Richter log model and the pH, the base is 10 because there's no base written. Whenever there's no base written, it's a base 10. The powers of 10 are what you're really concerned about because, as I showed you, if we did 10 to the 0 or 10 to the 1st or 10 squared, when we do log base 10 of 10 squared, that's 2. The 2 comes down, and then log base 10 of 10 is 1. Same way with 3. Same way with all of these values. So what's pH? That's a hydrogen ion concentration in particular liquids in moles per liter. It's very tiny amounts. So a logarithm function is going to be useful. What's the Richter log model? Well, it's the measure of the intensity of seismic waves, measured actually in millimeters. Those are shock waves. Divided by 10 to the minus 3, that's just sort of to center that at 0. And so the idea is all these exponents get pulled down in front, and then there might be some minor adjustment, like you see it multiplying by negative here so that you can make it positive. Here you're dividing by 10 to the minus 3 so that when you start with 10 to the minus 3, it's 0. So what's happening in this, let me get a couple of note cards, is that you just, it's all an exponent-based situation. So with your your pH model, so when you start with 10 to the minus 14, that's what goes into the negative in front there. That's what goes in. So that negative 14 comes down in front, and then you have log base 10 of 10, which is 1. So that becomes positive 14. The negative is just to make it a positive value, because it's just easier to talk about positive values. There's the concept of, let me put my other window back up here, of the pH model. 10 to the minus 14, that's a pretty tiny amount of hydrogen ion concentration. So we call that the most alkaline or basic of liquids. Kind of like drain cleaners or bleach or any of those, ammonia, very alkaline. When you get to 10 to the minus 7, measured in moles per liter, that's neutral, like pure water is the best. Blood is very close to being neutral. And then over here, battery acid. So as you increase the, well, this is 1/10. 10 to the 0 is 1, by the way. Anything to the 0 power is 1. So this is like 100% hydrogen ion concentration would be the most acidic. Again, logarithms are used to model data where the inputs, the x values, the independent variables are extremely small or extremely tiny, extremely large, like you have with the Richter log model. So in our Richter scale model, you have these millimeter seismic shock waves that get substituted in here. We divide by 10 to the minus 3, so there's a subtraction of exponents. So it's really like adding 3 to it, because when you subtract negative 3, you add 3. So 10 to the 4th goes in, that's, you add 3 to it, so it's really 10 to the 7th. And the 7 comes down, and you have log base 10 of 10. So it just provides a scale. So yeah, 7 earthquake is huge, 32.8 foot shock waves, 10 to the 4th millimeters. So I did some conversion there. Believe it or not, all of these have happened at some point in our career, or in our, I should say, our world's life. So 10 to the, this was an earthquake in Chile, the strongest one ever recorded. This one was an asteroid impact that supposedly killed the dinosaurs, if you accept that. Anyway, so just some good applications of logarithms. Again, used to deal with large powered data, usually the base is 10, and you're trying to look at those x values. Problem is that it's not very useful to look on a table on a calculator, because these values of 10 to the first, 10 squared, 10 third, there's not equal scaling between them. So it's just better to look at kind of the layout like this and to skip looking at the graph. But anyway, there's a couple of great applications of logarithms. And what I want to do now is get to our notes and then have you work from there. So learning target for today is to go the other way, solve logarithms with exponentials. Try to get my camera centered here. And you are going to want this right here, or we could be over here. And the whole idea is the base, focus on the base. Both of these become the exponent now. They go to the exponent position, and then your base is the base that you're looking at. So on number 1, what is the base? The base is 10. And then both of these go to the exponent position. You can write the base of 10 in there if you want. I kind of scrunch that up a little bit. You don't have to. So those cancel each other out. The x comes down, whatever this is, maybe that's an x plus 2, whatever it is, that will come down. This is 100. And I need to tell you this, you need to check your answers. You can't take a log of a negative number. So this cannot be negative on your input. It can be small. Don't get confused. These were just small numbers, but they're all positive. Actually, these are small numbers, but they're still all positives. You can't put a negative in there. All right, so on number 2, the base is 3, and then each of these are going to get moved to the power position. These cancel each other out, 3 to the log base 3. That becomes 1. That's the canceling effect. The x will come down, and then 3 to the 5th. Whatever that would be. Okay, now we've done it again. Trying to find my, there they are. I'll get the hang of this pretty soon. 243. So you'll not need your log base key today. You'll just need your power key because that's how we're going to solve these. And also, I haven't made a big deal. You need to get it in this form. You need to get it in this form. Just a single log statement on both sides. And note that we have an ln, which is log base e. Whoops, I meant to write e. That we need to divide by 2 on both sides. Move that up. ln is log base e, which is the natural exponent. So e is the base. And both of those move to the exponent position. So 3x equals e squared. And then you're going to divide by 3 to get your final answer. So e on your calculator is right behind the ln key. You have to search for it a little bit. Oh, let me move this down. So second function ln on the graphers, it's 2.71. So if you want to just take 2.71 and raise it to the first power, so whatever power it is, so you had to hear it, sorry, it's 2. You can do that. So e is 2.71. That makes it easier to do it. Divide by 3, and I had 2.5 on my answer key, but it's just a rounding thing. So 2.718. Let's try that, see what happens. 2.718. Yeah, a little bit better, 2.718. So e is that value. You're welcome to just do that also. It'll save a little bit of time. Base is 5. So each of these are going to go to the exponent position, and the 5 to the log base 5, that's going to cancel out. You're going to have x plus 1 equals 25, and then subtract 1. These are probably easier today because you don't have to deal with your log base key. And if you'll just do 2.718 for e, it's a lot easier. Notice you have log base 2 on both sides, and you do have your log statements alone. I haven't been saying that very much in this lesson, but you need to make sure that there's nothing multiplied in front, there's nothing added after them. There's some coming up, I think, where that's case here. So now you just remove the logarithms, or the base is 2. I'll always show this so you get the idea. So 2x is 100, and then x is 50. And these 5 are a little more involved. Some of them are going to give you a quadratic. So you're going to have to go back to quadratics, solving quadratics, and what that means. There's another set of parentheses here. Equals 2 to the 4th. So that just takes down x plus 4 squared equals 16. However you want to do this, I think one way that's rather clever, instead of foiling it out, is just to take it equal to, you're going to square root both sides. So it's going to produce these two equations. Kind of like we had, this was one of the ways we had of solving this. So square root both sides, and then subtract 4. There are ways of checking these, though. That way is to substitute in -8 plus 4. That's -4. -4 squared is 16. So log base 2 of 16 better be 4. This is where you would have to use your log base key. And then put 0 in, you get 16 again. 4 squared, log base 2 of 16 is 4. So you're checking this out. Is that true? That's the check. If you don't have the log base key, it's just log of 16 over log of 2. That's the change of base formula. So there's that. And then if you have a log base key, it's under math and then up arrow. It's 2, whoops, you need to do that, 2 and 16 that you put in. It's the same thing, just use a change of base. If you don't have an 84 or more or the 36x, you're going to have to do change of base, which is fine. Or just if you were solving an exponential and you had this answer, leave it. It's the answer. Okay, 7. So the base is 3, and both of these move to the power position. So it's just the left and right hand side go to the power position, and then the base is whatever the base in the logarithm is. The base is the base. X squared equals 9, and then just square root both sides. You get -3 and 3. And again, you can check that out by substituting back in. 8 and 9 are new as to what we need to do. It's not hard what we need to do. But you can't use these rules because I don't have a single logarithm statement on one side or on both sides. No good. So the next page in this deals with the laws of logarithms. When you add logs, you can make it into 1 by multiplying the indices, what you're taking the log of. You subtract logs. If it's the same base, you can divide the indices and make it into one log statement. That's very important. And that's what's going to happen on 8 and 9. I'm actually going to just do those simplifying steps right away. So log base 7, now we're going to multiply together the indices, the 4 and the x. And on 9, we are going to divide the indices. You have to make sure, though, that the base is the same. So you can't do that if the base is different. You're just stuck. You'd have to graph it and use a zero finder. Now we're here. We're at the point where we have a log on both sides. They go to the power position. You can skip that step if you know you're just setting the exponents equal to each other. There's no reason to write that. 8. Same way here, just skip the step. You know it's going to end up being that x plus 4 over 4. I'm sorry, 1. I have you guys that catch my mistakes all the time. X plus 1 over 4 equals 2. Multiply both sides by 4. And you get 7. Just checking things out here and making sure I'm not doing anything wrong. We're good so far. And last one. So each gets the exponent position with a base of 3. And so x squared minus 2x equals 3. This is a quadratic. Now we're going to have to find the zeros. And the way that we've done this in the past is to use our good old polysymbol. If you don't have that, you have to understand something, that the internet is just really powerful. And I want you to watch this. Let me try to, all right, this is my YouTube here. After I'm done uploading the window, go to a new, watch this. Solve x squared minus 2x minus 3 equals 0. Watch this. Bam, -1 and 3. People, the internet is more powerful than your graphing calculator. Use it if you have to. Okay, so -1 and 3 are the solutions. I'll write that down. I've also got a log base. You can actually get a log base calculator on the internet. Log base 7, you just type it in, of 49. That's going to be 2. 7 squared is 49. And it even does the graph. How cool is that? Graphs of logarithms. So we haven't talked about how graphs look. It's more important to understand the data side, like I had with the Richter scale and the pH. But they're flat like that. They're also in your notes. And again, make sure you download this first notes again, because I changed a few things. Anyway, back to our problem. Point is this: get on the internet. You can find a log-based calculator. You can find something that will take the place of the polysymbol app. You're not lost forever. Last 2 problems, and then I'll be done for today, and hopefully get to see you tomorrow. So remember to check your email tomorrow for the invite to the Zoom meeting. You don't have to come in to, you can just come and talk. That would be great. So here's the problem that I had in the notes. We have the hydrogen ion concentrate in moles, molar. I'm not really, it's capital M, moles per liter. So here's what we do. The pH is the negative log base 10 of 4 times 10 to the minus 8. So this is just, you're now going to use your calculator to do this, and it's not important to see those powers come down. Just do the calculation. That actually is the real blood to the -8. You can use the log base app site I showed you to do this too, or just type this in an internet search bar. There's the pH, 7.39, 7.40. You want to take pH to about hundredths place. So that's a little bit on the basic side. I don't think blood's a perfect, it's not like pure water. You want to have your blood alkaline, by the way, a little more alkaline, but not severely alkaline, just a little more than normal. That's probably a pretty good pH. And here's the earthquake. Magnitude of an earthquake is log base 10 of the intensity divided by 10 to the minus 3. Again, this is just to set it, the 10 to the minus 3 to be 0, because that's like the smallest earthquake. So here's what you're going to do. Log of 4567 over 10 to the minus 3, and literally just type that in. Log of 4567 over 10 to the minus 3. 6.7, pretty big earthquake. Magnitude. Oh, there we are. Seismic waves are just, they're energy waves. It's not like the actual Earth that's moving 4,567 millimeters. They're energy waves caused by movement of the tectonic plates in the Earth. But that is, useful because the I starts getting out of control. And again, the concept of logarithms is pulling that power down. It takes logarithms, take large values and small input values and crunches them down to tiny numbers. That's useful. And that's the sawtooth application. So you have your assignment. And again, if you need me tomorrow, I will be available. And have a great rest.